Hello everyone, welcome back. Today we're going to talk about projectile motion. Um, this topic really relates with the kinematics topic, so I suggest you go back and watch the other video. But still, we're going to first have a little introduction again to the notation so that you can understand even without watching the first video. So for silhouette, S is the displacement, U initial velocity, V final velocity, A acceleration, T time. I'm not going to spend a lot of time in this because we've already done this, but just to give you an explanation of the notation. So let's first start from the formulas. We're going to divide this into vertical formulas and horizontal formulas. Projectile motion is a motion that goes in 2 dimensions, so in a graph, both in x and y axis. As you can see, this could be like a projectile, so something that goes through here in 2 dimensions. And the y-axis is, of course, the height. So, for example, here it is the position, and it is the h, so the maximum height. Then we have time in the y-axis. As you can see, the graph forms a perfectly symmetrical parabola, and that's not going to be the same with air resistance, but we're going to talk about this later. So first of all, since we're going to talk about the vertical formulas, we need to know when using the vertical formulas, we have to use the velocities with the y component, so the vertical component. How do we know the y component? As for example, for Vy, Vy equals to V times the sine of the angle, for example, theta. The angle is at the angle from the horizon at which the vector of the velocity is. And of course, Ui equals to U times the sine of theta. There are two main formulas that actually, like, for example, are the same as the formula for kinematics, but here we're going to use them for the vertical component of the projectile motion. For example, the first one, the displacement equals Vy, so all of these velocities are the component, the vertical component, of course. So Vy squared minus Uy squared divided by 2a. In this case, A normally is G because it's vertical, so it goes through air, so it has the gravitational acceleration, the gravitational force, and the displacement, since it's a vertical, we can call it height. So the height equals to V squared minus U squared divided by 2A. Then we have AT equals V minus U. This was the main formula we talked about in the last video. And so from this, we can see that the time it takes to go up and down is equal to Vy minus Uy divided by A. And then A, again, is normally equal to G. Here, I want to do a remark. The time it takes to go up and down, it's also the time it takes, for example, the time it takes to reach the maximum height and go down again is the same time it takes the object to fall down even on the horizontal direction. I'm going to see this again, maybe in the exercises. Now we're going to talk about the horizontal formulas. You can see here, we can see the range and the velocity. So it's the same as before. We need to use Vx and Ux. So Vx and Us equals to V or U times the cosine of the angle theta. And here you can actually see the angle theta. What is it? So the range, so the displacement, that is actually the range because it's the horizontal, equals to V plus U. And remember, it's Vx plus Ux times T divided by 2. Now the T is the same T I used before if we're doing a problem, because at the same time the object falls at the same time both in vertical and horizontal. The displacement though is different. This is the range, the other one is the height. Now we're gonna see a little bit about the fluid resistant graph. So this is a graph that is plain. You can see the main parabola. This is like the height and distance, so the height, so the vertical, and horizontal, so the range. Without air resistance is a perfectly symmetrical parabola. So for example, the time it takes to go up is for the maximum point is the same time it takes to go down. With a resistance though, you can see the maximum height is uh, less high, is smaller. Here it's like half of it. I'm not too sure if there's actually half, but still it's a reduced height. And also the range is reduced, and you can see it's asymmetrical. So it takes much more time to go up than to go down. Why is that? Because air resistance um, is is trying to stop the projectile. And also here I wrote a little formula that is not really important because it's difficult, but still I wanted to put it. So the drag is like the Ft, so the force of drag equals to half of PV squared CdA. P is the density of the fluid, V is the velocity at which the object is going, CD is the coefficient, drag coefficient, so it depends on the surface, and then A is the area of the object. Terminal velocity. Terminal velocity is when, so if the drag equals to F being the force that is pushing the object. So for example, if a object is falling, F equals Fg, so the gravitational force. If the gravitational force is the same as the force of drag, the object is not going to accelerate anymore. It means that if there is no acceleration, there is a terminal velocity. For example, the rain. When water comes down, it is not coming, if you calculate without air resistance, it's going to come down really, really, really fast, and it may actually kill you. But since there is air resistance, water falls to a certain, go faster, fast accelerates, but then it stops to a certain terminal velocity. So terminal velocity is the maximum velocity attainable by an object as it falls through a fluid. Terminal velocity here I wrote as a basic formula. So we can just put F, so MA equals to the other formula that we did before, and it results in the square root of 2ma divided by PACD. The first A, so the acceleration, usually is g, because usually you look at a falling object that, for example, yeah, falling object, so it reaches the terminal velocity, but I still put A because, for example, for cars, the F could be the engine, so the force that the engine is providing, and the drag can also be horizontal, and so A is just the acceleration of the car, not of the g. There is then the graph. As you can see, the graph is accelerating until it stays at a certain terminal velocity. Let's do some exercises now. So a stone is thrown horizontally at a speed of 5.0 meters over second from the top of a cliff 78.4 meters high. How long does it take the stone to reach the bottom of the cliff? How far from the base of the cliff does the stone strike the ground? What are the horizontal and vertical components of the velocity of the stone as it hits the ground? What is the final speed of the stone as it hits the ground? So what it's asking is the first is asking the time. Second is asking the range. Third is asking what are the horizontal, so the components, so Vx and Vy, and then the V. So a stone is thrown horizontally at a speed of 5.0, so we can understand that Ux equals 5.0 and Uy equals to 0 because it's not thrown up or down. So Ux equals to 5.0, Uy equals to 0, height 78.4, and we are asked the time range Vx, Vy, and V. So I started here by saying this is really important to understand. Since in these exercises we're not using air resistance, the velocity Ux will be the same as Vx because in the horizontal point of view, the object is not slowed down by anything. There is no air resistance. So there is the gravitational force that is putting down, but horizontally just going and going and going. So Vx equals Ux, so we already know Vx, that is equal to 5. Now, to calculate the height, to calculate the the Vy, we can use the formula used before. So we said before in the formula, we said the height equals to V squared minus U squared divided by 2A. In this case, I will say A is equal to G. So if the Vy equals square root of 2GH plus Uy squared, since Uy is equal to 0, Vy equals to square root of 2GH. And this formula that we derived is going to be the same as when we will be using energy and the work. So still the square root of 2GH, so 2 times 9.8 times 78.4, and the square root is 39.2 meters over second. So we know now the Vx and Vy. I calculated V at the bottom, but we can actually do it now, so it's pretty easy. We just use the Pythagorean theorem. So V equals square root of Vx squared plus Vy squared, and that is equal to 39.52 meters over second. Then I calculated the time. So the time it takes to get on the ground. Here, okay, I made a little mistake by in the formula because time is equal to Vy minus Uy divided by G, not Ux. So it's Vy minus Uy divided by G. So the difference in the speed divided by the acceleration. But the speed are the vertical, not Ux, Vy. So it's 39.2 minus 0 divided by 9.8, the acceleration. So it's 4 seconds. Remember, 4 seconds to go up and down, or in this case just down, is the same as 4 seconds to go horizontally because it touches the ground in just one time. So the range will be equal to Vx plus Ux times the time divided by 2. So 10 times 4 divided by 2, so it's 20. So from this exercise, we finished, and just a little remarks. First of all, the most important thing to understand is that the horizontal velocity without air resistance are the same. Next thing is that the time is the same also because a ball, or like in this case a stone, is at the same place at the same time. It cannot be in two places at the same time, so at the same time it falls into the ground. And then when it's asked the final speed and you have the two components, you can just use the formula square root of Vx squared plus Vy squared. So to do these problems, the most important thing is to divide the vertical and horizontal components and use the formulas. That's it for this video. We'll see you again in the next video, maybe with the friction. Thank you.